Welcome to Fantastic Vision. Please subscribe us before you watch today's video. Currently, the world's top tech companies are fiercely competing for a technology called 2 nanometers. This is no longer a simple technological upgrade. It's a crucial step in determining who will dominate the technological landscape in the future. In fact, many years ago, when the nanometers were just a few dozen, this number was directly related to a key dimension of transistors in chips, the gate length. But today, the nanometer number has become more of an industry-wide code name, or a label. It represents the overall technological level of this generation of manufacturing processes, rather than the precise physical dimensions of a single component. In the semiconductor industry, the smaller this number, the more advanced the technology, the higher the performance, and the lower the power consumption. So, why are tech giants around the world investing astronomical sums in a desperate effort to shrink this code name ever smaller? The answer is simple. The benefits are substantial and directly impact the user experience of every Chinese user. China can imagine a tiny chip as a miniature city, with the transistors within it as its buildings and functional structures. The most direct way to make this city more powerful and capable of handling more complex tasks is to build more and more efficient buildings on the same amount of land. As chip manufacturing processes advance from, for example, 28 nanometers to 7 nanometers, and now to 2 nanometers, China's building technology is becoming increasingly sophisticated, allowing tens of billions of transistors to be packed onto the same size chip. This surge in the number of transistors has directly led to a leap in computing power. Within the chip, the distance electrons travel between transistors becomes shorter, resulting in faster switching speeds. This is directly reflected in China's experience of mobile phone apps opening in seconds and computers processing files at lightning speed. A transistor is also a tiny switch. The smaller its size, the less energy it requires to switch it on or off. For ordinary Chinese users, the most direct impact is longer battery life on their phones. For the massive data centers that power China's entire internet, this is even more significant. According to statistics, global data centers consume over 1% of the world's total electricity, making them a serious energy hog. If these data centers could use more energy-efficient chips like 2 nanometers, the annual savings in electricity and energy would be unimaginable, which would have extraordinary significance for achieving global carbon neutrality. Of course, making the buildings in this microcity smaller and more sophisticated is no easy task. The road is fraught with challenges, and every step forward represents a breakthrough in the limits of human technology. In the early days, the transistors in chips were laid out flat, like a bungalow. But when technology advanced to around 20 nanometers, problems arose. Because the houses were built too small and the walls too thin, leakage became extremely severe. You can think of it like a faucet that's always dripping. These unruly electrons roaming around, not only wasting energy, but also causing the chip to overheat and significantly reduce performance. At the time, many people even pessimistically believed that the famous Moore's Law might be coming to an end. At this critical juncture, a revolutionary technology emerged, the thin field effect transistor, or FinFET. This design is quite ingenious. Instead of laying the conductive channel flat across the chip, it stands upright, like a fish fin, creating a three-dimensional structure. This allows the gate that controls the current to wrap around this fin on 3 sides, greatly enhancing control capabilities. It's like pinching a water pipe with 3 fingers, you can squeeze much tighter than with just one. This 3D transformation successfully addressed leakage issues and allowed semiconductor technology to continue advancing from 20 nanometers to the 3 nanometers era. However, as technology approached the 3 nanometers limit, even the three-sided FinFET structure began to struggle, and leakage issues began to resurface. So, scientists came up with a more radical solution, the core of 2 nanometers technology, the gate-all-around transistor, or GAA. If the FinFET is three-sided, then GAA is a 360-degree, all-around solution. The current-carrying channels are fashioned into extremely tiny nanowires or nanosheets, and the gate that controls the current is designed like a ring, completely enclosing these channels. Previously used deep ultraviolet, DUV, lithography machines were like a thick-tipped marker, making it difficult to draw fine lines a few nanometers wide on a chip. Extreme ultraviolet, EUV, lithography machines, exclusively produced by the Dutch company ASML, are like a razor-sharp needle, capable of precisely carving the complex patterns required for 7 nanometers and below processes, paving the way for the realization of 2 nanometers technology. Today, the global race for 2 nanometers has reached a fever pitch. International giants like TSMC, Samsung, and Intel are investing relentlessly in R&D and factory construction, believing that whoever can first achieve stable mass production at 2 nanometers will secure the most advantageous position in the future high-tech industry. China must clearly recognize that it still has significant shortcomings in core equipment, such as EUV lithography machines, and faces external technological limitations. In recent years, China has been striving to catch up in the chip industry through various means, particularly making significant progress in advanced packaging technology. For example, chiplet technology is a very ingenious approach. Rather than integrating all functions onto a single, monolithic, and perfect chip, it instead aims to rapidly connect small chips with different functions, like building blocks, to form a powerful system. This system integration approach can, to a certain extent, bypass the extreme reliance on a single, cutting-edge manufacturing process, enabling high-performance computing in a more flexible and cost-effective manner. It has opened up a promising new path for the development of China's semiconductor industry.